Hi, this is Jeff Spence, your Math 120 instructor for the Community College of Denver, and this is our video lecture over Section 8B, doubling time and half-life. So we're looking at exponential growth, where we're going to figure out certain substances or certain things doubling time, and exponential decay, where we're going to look at the half-life of a certain substance or a population of things. So the time required for each doubling in exponential growth is called the doubling time. So how long it takes for it to go, or for it to be twice the size of what it used to be. Half-life is just the time required for each halving in exponential decay. So we use this a lot when we try to date archaeological sites using what's called carbon dating, and we use the half-life of carbon to figure out, which is a very, very long time to figure out the age of, say, archaeological sites or dinosaur bones or things like that. So doubling time, after a time t, an exponentially growing quantity with a doubling time of t double increases in size by a factor of 2 to the t over t double. The new value of the growing quantity is related to its initial value at t equals 0 by the new value equals the initial value times 2 to the t divided by t double. So this part right here is an exponent with a fraction. Our initial value will be easy to find. Just have to make sure that we're putting in the right values for our exponent. This would be a formula that I would write on the formula sheet on your notes for the exam. So compound interest, let's look at an example, produces an exponential growth because an interest-bearing account grows by the same percentage each year. So that's definitely exponential growth. Suppose your bank account has a doubling time of 13 years. By what factor does your balance increase in 50 years? Well, the time to double is 13 years. We were given that. So after 50 years, your balance should increase by a factor of, well, let's figure this out. So let's just talk about this logically. All right. So by what factor does your balance increase in 50 years if it doubles every 13 years? Well, it should double in the first 13 years and then double again in the next 13 years, which is 26 years, and then double again after the 39th year, and then it would double again after the 52nd year. I'm just adding 13 years each time. So it's going to double a little less than 4 times. That's why we take the time and divide by t double, because we want to figure out how many doublings it's going to go through in this amount of time. So in 50 years, if we divide that by the amount of time that it takes to double, it will go through 3.8462 doubling times. So 2 to the 3.8462, it will grow by a factor of 14.382. So if we started with a balance of 1,000 in 50 years, we would take 1,000 times 2 to the 50 over 13, which we found was 14.382, and we would have $14,000 and $14,382. So generally speaking, whenever we want to find the t double when we have a growth percentage, then we can use this, what's called the rule of 70. It's an approximate rule. It's a very nice rule. And the doubling time is approximately equal to 70 divided by this percent. This approximation works for small growth rates and breaks down for large growth rates, but usually we have generally small growth rates when we're looking at exponential growth. And then our formula is our new value equals our initial value times 2 to the t divided by t double. We already had that formula back here. Okay, so let's look at a couple examples here. Let me go back one. All right, so in 2013, the estimated world population was 7.1 billion. Using a doubling time of 61 years to predict use a doubling time of 61 years to predict the population in 2024, 67, and 2122. Okay, well, if the doubling time is 61 years, then, and I want to figure out the population in 2024, that will be 11 years after 2013. I just subtract those and I get 11 years. So the starting population is 7.1 billion. So using my calculator here, I'm going to use my formula. Let me show the formula again. My initial value times 2 to the time, which is going to be 11 years, divided by the time to double. So 7.1 billion, 7.1 billion, let me make sure I'm typing this right here. Okay. 7.1 times 2 to the, and when I type this fraction here, I'm going to put parentheses, okay, to the time. Now remember, the time that it has passed is 11 years. 2024 minus 2013 is 11. And we're going to divide that by the time to double, which was given to us as 61 years. So divided by 61, enter it in, and it says round to 1 decimal place is needed. So this will be 8.0 billion. 8.0 billion. All right, let's do one more. So what will the population be in 2067? We'll have to figure out how many years have passed. So 2067 minus 2013 is 54 years. So I'm going to use the time of 54 years, but everything else is the same. So I'm going to do 7.1 times 2 to the parenthesis. Now we're talking about 54 years is the time that it has elapsed, divided by the doubling time of 61. The world population will be about 13.1 billion. All right, let's look at another example here where we're actually going to use the formula here, where we're actually going to be given a percent. We're going to find the doubling time. It just wasn't given to us. And then we're going to actually use the formula again. So let's look at this example. It says use the approximate doubling time formula, rule of 70, so 70 divided by the percent, and discuss whether the formula is valid for the case described, so just if the percent is under 15. So an economic indicator is increasing at the rate of 6% per year. So that's less than 15, so we can use this formula. What is its doubling time? By what factor will it increase in 3 years? So what is the doubling time? We take 70 divided by 6. 70 divided by 6. This is the only time we actually don't convert the percent into a decimal, and it's 11.66. And let me just make sure that decimal rounded to the nearest tenth. Okay, so its doubling time should be 11.7 years. Okay, by what factor will it increase in 3 years? So that means that I don't have a starting value, so I just take the starting value, you could just say is 1. So 1 times 2, using the formula, we're doubling, to the, and how many years? 3 years. So 3 divided by the doubling time of 11.7. And this will tell us how much it's grown by. It will grow by a factor of 1.19. To the nearest hundredth, that's just 1.19. So it'll grow by 1.19. Is this formula valid? The answer is yes, because we're growing by 6% per year. Okay, let's look at this example. It says use the approximate formula, the rule of 70 for the case described below. Discuss whether the formula is valid. Gasoline prices are rising at a rate of 6% per month. What is their doubling time? By what factor will prices increase in 4 years, 9 years? Oh, we've already done this problem, so I'm going to move on. Okay, so I thought that was a little different problem, but it's the same. All right, so let's also look at I've done these examples. Oh, okay, sorry. No, I have not done this example. Okay, world population doubled in the 40 years from 1960 to 2000. What was the average growth or average percentage growth rate during this period? So now we're given a doubling time, and we want to figure out the growth rate. So if we go back to our formula, the rule of 70 says the time to double is 70 divided by p. So we're given that this is 40, and we need to solve for the percent. And there's a little algebraic trick when you're solving for this. If I multiplied both sides by p, then it would be p times t double equals 70, and then I divide by t double. They essentially just switch spots like it is right here. So whenever we want to solve for p, we can just switch them and take 70 divided by the time to double, which is 40. 70 divided by 40 is 1.75% per year. So the average population growth rate between 1960 and 2000, since it was taking 40 years to double, we took 70 divided by 40, got 1.75 growth percent per year. All right, now let's look at half-life. Half-life is very similar. We're going to solve these problems very similar to doubling time, except for that we're going to multiply by 1/2 because we're decaying versus multiplying by 2 in the formula. So this formula is very similar to the last one. We have the new value equals the initial value times 1/2 to the t divided by t half. The previous formula was the new value times equals the initial value times 2 to the t divided by t double. So basically it's just the matter of, are we doubling, we're multiplying by 2, or are we halving, we're multiplying by 1/2. So suppose that 100 pounds of Pu, some element Pu 239 is deposited in a nuclear waste site. How much of it will still be present in 100 years or 100,000 years? So we have to know the half-life, and the half-life is 24,000 years. Given an initial amount of 100 pounds, the amount remaining after 100 years is, okay, so the new value, that's what we want to figure out. We're going to use our formula here. So our initial value is 100 pounds times 1/2 to the 100,000, that's the amount of time, divided by 24,000 years. And I'll type that in the calculator to show you. We take 100 pounds, we take it times 1/2 or 0.5 to the 100,000 years divided by 24,000 years is the half-life. And we get about 5.6 pounds left. 5.6 pounds left. That's how they got that answer. Okay. So for a quantity decaying at an exponentially, so let me do another example in homework here. I'll do those notes in a minute. I think it was 17. Okay. Use the approximate half-life formula below. Discuss whether the formula is valid. So urban encroachment is causing the area of a forest to decline at 10% per year. What is the half-life of the forest? What fraction of the forest will remain in 30 years? So the half-life is just 70 divided by 10. Using our formula here, 70 t half is just 70 divided by the decay rate. So 70 divided by 10 is 7 years. That's the half-life. So after 7 years, the forest will be half the size that it was previously, which is pretty amazing. That's pretty quick. What fraction of the forest will remain after 30 years? Okay, so we have to use our formula here. Our new value, how much of the forest will be left after the initial value times 1/2 after 70 years? So we're going to do, in our calculator, we'll just say that 1 is the initial value if we're not given an initial value, times 0.5 to the amount of time that's elapsed, which is 30 years, divided by the half-life time, which is 7 years. And there should be about 5%. It says type an integer or decimal rounded to the nearest hundredth or thousandth. So this would just be 0.05. What fraction, 0.05, of the initial value will be left? What fraction of the forest will remain in 30 years? Type an integer or decimal rounded to the nearest thousandth. I did 30 divided by 7. What fraction? My answer was that I wasn't rounding to the nearest thousandth, I was rounding to the nearest hundredth. So the answer would have been, if we rounded to the nearest thousandth, would have been 0.051. They were looking for 0.051 and I gave 0.05, so excuse me there. So remember now, when we do these problems, we're going to have basically two formulas that we're going to be looking at here. Well, 4 formulas, I guess. So the time to double is always 70 divided by the growth rate. So if they don't give you the time to double just in the problem and they give you a growth rate, you'll have to do this division. Then you use the new value equals the initial value times 2 to the time divided by t double. I would write both of those blue formulas down in your formula sheet. Then for half-life, It's the same thing. If we have a half-life, the rule of 70 still applies, and we're using the formula where we use the initial value times 1/2 to the time divided by t half. And that will give you the fraction that's left after a certain number of years. Good luck, and we'll see you next time.